Hello, welcome back to this fourth lecture in Tribology course. Today we'll be talking about friction. As we have discussed earlier, friction, while sometimes useful and even essential, limits the efficiency of machines. Walking, crawling, or running would be impossible without friction. As we have discussed earlier, that the earliest human civilization depended on fire produced by friction due to rubbing of sticks or flint stones. Ancient civilizations such as Egyptian also faced the difficulty in dragging or rolling heavy objects during construction of pyramids or positioning of heavy statues. Friction is an interfacial phenomenon when two bodies slide against each other under load. And the exact understanding of friction requires insight into contact mechanics, lubrication, chemistry, frictional heat generation, and its subsequent influence on metallurgical changes of material and many other aspects of materials and mechanics in macro, micro, and nanoscales. We shall touch upon some of these points as we go ahead in this lecture. So we go to the main discussion. But before we go to the main discussion, it will be inappropriate to start the discussion on friction without the mention of Leonardo da Vinci, who lived in Italy during 1452 to 1519. And we know him as a painter, but it is surprising to know that he can be named as the father of modern tribology. His work on friction originated from his studies of the rotational resistance of axles and the mechanics of screw threads. His manuscripts, we have found it in many various museums, and sketches, some of it is shown above, implies that he understood the laws of friction and applied them to various mechanical problems for over 20 years. So we can easily conclude that he was probably the father of modern tribology. Some of these points are available in the paper written by I.M. Hutchins in Ware 2016. The details are given below. So with this note on Leonardo da Vinci, we proceed to see who else has contributed in the development of frictional theory. The next we can think of is William Amantin in 1699. He was also a Frenchman, and he looked into the dry friction, and he concluded that friction is independent of contact area and is proportional to direct load, that is the load P in this picture here. So this is a very well-known picture that as we drag or pull or push an object on a platform, then frictional resistance is produced, and usually it is proportional to the load on it. And it is independent of contact area. This is something which needs little thinking. If we look back to our the the picture that we have seen many times, this red and blue surfaces, rough surfaces, rubbing one onto another, we see that the contacts are only on few points, not on the whole surface. Therefore, the friction must be dependent on only the area which is in real contact. So here we distinguish between the real area of contact and apparent area of contact. So obviously when Amundsen looked into the problems of friction, he considered the apparent area of contact. And obviously he found out that it is independent of the contact area. Leonard Euler was a very well-known mathematician who lived in 1707 to 1783. He also looked into this problem and he agreed with Amundsen more or less on the same points. Then comes Coulomb, Charles Augustine de Coulomb, who lived in 1736 to 1806. And he also found out that frictional force is proportional to load. But in addition, he found out that it is independent of sliding speed. This is an additional information. Some idea of roughness hypothesis also was given. This means that if the surfaces are rough, friction will be rough. This is usually observed that if we rub two smooth surfaces, friction is less. But if the roughness is high, friction increases. This was the idea in those days, was that one surface has to ride over the roughness of the second surface, and hence the energy lost comes as the friction energy. But we'll see later on, this is not the only reason, there are many more reasons. But it is true that the rough surfaces offer higher resistance and the friction is more. Then we go to J.A. Ewing, who lived between 1855 to 1935. He came up with the idea that friction is a result of molecular forces, surface molecular forces, and this leads to adhesion hypothesis. This is probably true to some extent, but it does not apply to all conditions and all surfaces. Adhesion, if we think of adhesion, and it must be due to the intermolecular forces of the surfaces, then the surfaces have to be smooth and free of contamination. Had he supported this, had he in 1920 supported this adhesive hypothesis, but he came up with these 2 points, that the surfaces must be free of contamination and must be smooth. This is because both these points, both these parameters do not allow the surfaces to come close enough for the intermolecular forces to be operative. Therefore, for adhesive hypothesis to be true, one has to consider the surface contamination and surface roughness. Around this time, in 1938, 40, and more, and further, Bowden and Tabor in Cambridge contributed immensely into our understanding of friction. Their main contribution, or one of the main contributions, was to distinguish between the real and apparent area. As we have seen before, that when the two surfaces are in contact, contact is over the very minute portion of the surface, because the contact occurs at the peaks of the asperities, and hence what we call contact area is an apparent contact area, and the real contact area will be only the areas where the surfaces really do meet. And this, we'll see later on, makes a big difference in our understanding of friction. Finally, before we go further, we must repeat that friction is mostly undesirable. But as we have seen before, that it is sometimes very useful and essential, even in machine parts like tires and brakes, and many other machine parts depend on friction. With this introduction, we'll go to the laws of dry friction. It is important here to understand that friction, when lubricated and when it is not lubricated, are different. So here we consider only the dry friction. And it is well known that frictional force is equal and opposite to resultant applied force, as shown in the figure. This is generally true, and we all accept it, but there are exceptions. For example, you have a block on a plane surface, and you are trying to move it. And suppose you are unable to move it, that is, we apply an insufficient force to cause sliding. Then what happens? What happens to the energy spent on it? We cannot call that a frictional force because it is not sliding. So this force actually is not wasted. It goes in micro displacement at the contact, time-dependent displacement at the contact that we don't see. So once that displacement goes on and the force increases to a threshold level, then the object starts moving and we call it sliding. This is something like static friction and sliding friction. So before the force, threshold force is obtained or reached, it will not move. And so the frictional force is equal and opposite to resultant applied force. May not be true in all cases. Another point to remember is that if we try to move a body on a surface with machine marks, as shown in the figure, the body may not move in the direction of the applied force because it will have a jerky motion depending on the machine marks on the surface. So it's a clean statement like frictional force is equal and opposite to resultant applied force needs to be stated with certain caution. Then we come to the second law, and that is also quite well known. Frictional force is proportional to normal load, and we all accept it without any hesitation. This means that the coefficient of friction mu, as shown in the figure, is constant with load. So F, and we say F is equal to mu W. But this may not also be true in all cases. For very hard material like diamond and very soft material like PTFE, this may not be true. Experiment shows that we can write F is equal to CW to the power x other than mu WX and mu W. So if x is 1, it reduces to F is equal to mu W. So then the constant is the coefficient of friction. But if x is not 1, then we cannot call it coefficient of friction. We call it some constant, frictional constant, say C here. So F is equal to CW to the power x. Experiment shows that PTFE, sliding of PTFE against steel, this x is equal to 0.85. And we do not get a constant coefficient of friction, as shown in the picture. Third point in this is that a hard surface layer on a soft substrate. This happens even without coating. Usually people think of coating and other things. But even if without coating, we may have a surface layer by oxidation or deposition of surface atmospheric contamination. So when we slide two bodies with a skin or layer, then at light loads, the layer is not damaged. And that acts as a lubrication or lubricant layer, and the coefficient of friction remains low, as shown in the picture. But once that at high load, that skin or the layer is damaged, then the friction may rise, because then it is in contact with the original surface, and depending on the type of the material, the friction may rise. So there will be a change in friction. Here I've shown it increasing, assuming that the two surfaces are of different types. So when the skin or the surface layer is damaged, then the coefficient of friction may rise. So these are some of the deviations that we must consider when we say that frictional force is proportional to normal load. Usually it is, but there are exceptions. Then we come to the third point, which has been mentioned by many people like Coulomb. Friction is independent of apparent area. And this again is very true, provided we do not distinguish between the real area and apparent area. It will be dependent on real area. But if we look at the apparent area of contact, then it is independent. But this again cannot be stated categorically, because this will not hold if the surfaces are very smooth, because there the apparent and the real area of contact are almost same. So friction is independent of apparent area of contact is true unless the surfaces are very smooth. Then we come to the fourth law. The frictional force is independent of sliding speed. This again is true and has been found in many experiments. But consider static and kinetic friction. If we push or pull a body, then initially frictional force will increase until a threshold point, and then at the threshold point it will start sliding and the friction remains constant. So independent of sliding speed is true once the sliding starts, but not before that. So to categorically state that the frictional force is independent of sliding speed has to be taken carefully. Then there may be another point that if we take two steel balls sliding with increasing speed on copper or bismuth, then it has been found that the coefficient of friction drops as the speed increases. The experiment was usually done by allowing the two balls to slide along an inclined plane made of bismuth and an inclined plane made of copper. This is because as the speed increases, the contact temperature rises. We'll discuss briefly about the contact temperature later on. But this makes a big difference in the contact phenomena, because as the contact temperature rises, metals like copper and bismuth may have local melting. And this local melting would allow the molten metal to act as lubricant, and therefore the friction will come down. So to state categorically that frictional force is independent of sliding speed will be true, provided these situations do not occur. Okay, so these are the four laws we have discussed. Now the fifth law, effect of surface roughness. Now if we look at the variation of coefficient of friction with the roughness, we have written here CLA in the x-axis. We'll see that it normally is very high when the surfaces are very smooth. Then it comes down and then it remains constant over a range. And then at very high roughness it rises. This is what we've been discussing some time back. When the surfaces are very smooth, intermolecular forces and adhesive friction occurs. Intermolecular forces will be operated and adhesive friction will come into play. Then the friction will be very high. But when the surfaces are a little more rough, I mean not rough to that level, but not in the atomic level, then the friction starts falling because it is no more in the intermolecular layer and the adhesive friction is not in action. Then it will fall and it will remain constant over the range, And then when surfaces become very rough, then some other mechanism of friction comes into play. Then the one surface has to slide over another, and then maybe local welding of the asperities and many other mechanisms may come into play, and friction will rise. So very smooth surface friction is high. At the middle level, friction will be more or less constant, and at very high roughness, friction will rise. I think it is relevant to talk about Bowden and Tabor's adhesion friction theory at this stage. We have seen this figure again before, that when the two rough surfaces are in contact, the contact is at the peaks of the asperity. Now, if this happens, at the peaks of the asperities will only take the load. So obviously the load is concentrated on a very small contact area, and that causes a very high localized pressure, and this will lead to plastic deformation. And we may also call it plastic or pressure welding. So the points where they meet, like the points shown here, and here, there will be adhesive bonds or pressure welding, and the force required to break these bonds will be frictional force. Otherwise, you cannot move one surface against another. These bonds have to be broken. So this is probably one of the greatest contribution in understanding adhesive friction by Bowden and Tabor, that when pressure welding occurs at the peaks of the asperities and the force required to break them, we can, or the sum of the force of all the asperities, breaking all the asperities, would be the frictional force. So this probably is relevant to our consideration of friction, variation of friction with roughness. So we can summarize that there are basically three laws of dry friction. One is friction is proportional to normal load, except some few points we discussed earlier. Friction is independent of apparent area of contact and apparent area of contact. Again, there are some exceptions we discussed earlier. And friction is independent of sliding speed. Again, there are some exceptions. But these are the normally accepted laws of dry friction. Okay. Now we go to the friction measurement. This is the first measurement technique shown is very old and is probably taught in the school, that if you take an inclined plane and let a mass move along that depending on the inclination, as we tilt the table, at some point it will start sliding, and that will give us the force of friction, and we can find out the coefficient of friction. Consider the figure at the right. A block is shown here, resting on an inclined plane. The load or the weight of the body, W, has two components. One is perpendicular to the surface, which is W cos theta, cos alpha, and one is parallel to the inclined plane, W sin alpha. Now the frictional force, which is the applied force, is up the inclined plane, and friction will be down the inclined plane. So the frictional force F will be P minus W sin alpha. So mu is simply P minus W sin alpha divided by W cos alpha, which is the normal load. Now here, one may ask a question, why don't we do this experiment on a flat table, like the one which Leonardo da Vinci did many hundreds of years ago, or many people have done it. You take a block on a table and tie it up with a rope, with a pulley at the end of the table, and hang some weight. As you increase the weight, at some point, it will slide. So this does not require any inclination. But look at this equation in the bottom of the page. Mu is equal to P minus W sin alpha by W cos alpha. Here you have got two variables, P and alpha. So you have got a better control over your experiment. You can either vary P of the load or the weight that you are hanging from the pulley, or you can change alpha. It is easy to change alpha or the inclination of the table, and this experiment is simple and fairly accurate. But then there are more sophisticated instruments and apparatus available these days. We'll consider only one of them now, and this is called pin-on-disc apparatus. Pin-on-disc apparatus is simply what it says. It is like a gramophone record player. You take a disc as shown on the top left-hand corner of the slide. You have a disc and a pin pressed on the disc, and you rotate the disc like here. Like here, you rotate the disc. So as you rotate the disc and the pin is loaded on the disc, there will be friction and wear also, but in this picture we'll consider only the friction. Friction will be generated, and depending on the material of the disc and the pin, we can find out the friction of, when we say friction and wear, it is always a combination of material. So if we say the friction of steel, it does not make any sense. We must say friction of steel against copper, friction of steel against bronze, friction of steel against some other polymer or something. So it is a combination of material. So if we change the pin material or the disc material, we can find out the friction. Now, how do we measure the friction? Look at here. There is a loading bar here, pivoted here, and it is loaded here like this, simplest way. And as it is loaded, the pin applies a force on the disk, and the force applied can be measured in the loading pan, and the force, frictional force, can be measured fairly accurately by putting a load cell which measures the tangential force. That means how much is this bar moving transversely. That can be measured by load cell. And if we want to measure the wear, we have a LVDT or displacement transducer, which measures how much it has dropped, and that means how much the pin has dropped. So the amount of wear can be found out by the displacement transducer, and the frictional force can be measured by a load cell. In addition to this type of experimental apparatus gives us many other opportunities. Like if we put a camera here, infrared camera, then we can measure the radiation, infrared radiation. That will be a function of the temperature that is developed at the end of the pin. This is because as the rubbing goes on, frictional heat will be generated, and both the disk and the pin will be heated up, and we can find out the temperature, and hence the heat developed. There are many details of this, because one would say that for infrared radiation may not be sufficient for any combination of materials. So usually sapphire and other materials, diamond, other materials are used. And then by proportion, generated for other combinations are obtained. But anyway, this is just a method shown here that you can put an IR camera, infrared camera, and measure the heat generated at the contact. So this is a fairly useful apparatus, and there are many different versions of this available in the market. Although I think very few of them will give you opportunities for measuring contact temperature, but this can be arranged. So this is one of the widely used apparatus for measuring friction and wear also. But here we'll consider only the friction. And here the pin, the friction at the pin and the contact between the disk and the pin can be measured by the load cell here, as I said. Now, with this, there are many other sophisticated instruments, but they are all more or less in this, follow this principle. Now we'll briefly look at the approach, a simple approach to adhesive friction. Friction can be of many types: adhesive, abrasive, corrosive, erosive, and other types also. But here, we'll take a look at the adhesive friction. Let's consider a conical object with a hemispherical end and press it on a flat surface. When we do that, we get a contact surface of 2A. That is contact radius of A. So here, if it is a plastic deformation, then the load P divided by the area AR, real area of contact, is equal to PM. Here PM means flow pressure or hardness. And that is simple. We all agree with this. Load divided by the real area of contact is hardness, which is usually 3 times yield stress in uniaxial compression. Then we apply a tangential force here. So when we apply a tangential force, then the yield, the tangential force times the yielding will occur due to the combination. Yielding may occur due to only normal load. Yielding may occur in combination of tangential force and normal load. So here we consider that yielding will occur due to normal load when it is applied here, and yielding will also occur when we apply a tangential force. So the frictional force will be shear yield stress times the real area of contact, because we have assumed that yielding will occur due to frictional force also. So the coefficient of friction is F by P. F is the frictional force, P is the normal load. So what is F? F, as we have said here, is real area of contact times yield shear stress. And P is the normal load, and normal load is real area of contact divided by the PM, or the hardness. So real area of contact goes away, and we have tau y by PM. Tau y is the shear yield stress, and shear yield stress, as we have seen here, is compressive yield stress divided by 2, this one. So this is sigma c by 2, and PM, or hardness, is 3 times yield stress, so 3 times sigma c. So that gives us 1 by 6. This does not necessarily mean that in all cases of adhesive friction we'll get the friction of coefficient of friction of 1 by 6. The very simple approach to show that as we apply the normal load, there is a plastic deformation, and as we apply the frictional force, that will also cause yielding at the contact, and we use these two to find out the coefficient of friction. This will be true only for very ductile material where hardness is 3 times the yield stress, and yield stress in compression is twice the shear yield stress. For ductile material, this is quite true, and PM, or the hardness, 3 times the yield stress in uniaxial compression is also true. So for that matter, for this kind of material, we can safely say it is 1/6, but this is not a sacrosanct. It does not apply everywhere. It's just to explain what an adhesive friction is. So we'll stop here today. We'll take it up more in the next class.